Morning, everybody. Welcome from the land of the viral quarantine. Sorry that I can't be there this morning, but I want to talk to you for a few minutes about how energy and how we use energy sources and fuels to produce electricity. And so what I'm going to do is email you the notes that I have here and the links that I'm using with the videos as I talk you through it, and I would ask that you make notes. The good news is if you get tired of me, just click that little mute button on YouTube and you're all set. The bad news is it makes questions a little tougher. If you do have questions about today's lesson, feel free to send me an email and I'll get back to you as quick as I can. All right, so let's take a look at this. This is how energy is produced. So what we have is you had a number of presentations Monday on different sources of energy, from solar to hydro, which is water, fossil fuels, different ways that different fuels are sources of energy. Okay, and in most cases, with the exception of solar, most energy takes a magnet and spins it, or takes a coil like a wire and spins it in a magnetic field. Most of the time it's a magnet that spins, though, inside of a coil, and that spinning magnet induces or creates electric current. It creates electricity. And so what I want to do is show you how that works. Okay, here's a little cartoon version of a thermal power plant. It could be coal, it could be nuclear, anything that uses steam to turn a turbine. And so what they've done is they heat up the water, and the water produces steam. Okay, and then the steam takes these cogged wheels and turns them. Okay, so the turbine, it turns and turns and spins, all right, and creates circular motion, which then goes down a main shaft, and this is connected to a magnet, and it causes the magnet to spin very, very fast. Okay, this spinning magnet, what it does here, this doesn't, okay, well, the spinning magnet, what that does is it induces a force. Remember, we learned about magnetic field and force on electrons. Okay, and here's how it works. If you look here, we have this is the opposite. This is a magnet that's not spinning, and we have the wire that is spinning. Okay, inside this wire is electrons. Okay, and the electrons on their own, they don't move. But this wire, it's in a coil, and it's spinning because of the steam and the turbine that's connected to the steam. So the steam turns the turbine, and the turbine's connected to this coil. All right, and that therefore, of course, makes it spin. So as it spins, you look at this one, it gets close to the south and then goes down close to the north, comes up close to the south, comes down close to the north. And so the electrons on that wire experience a changing magnetic field. All right, I'll show you. It goes south, north, south, north. Okay, so that changing magnetic field causes a force. Remember, we learned about magnets and force before? We used the right-hand rule, and we said that what happens, hang on, I've blown it up too much here. There we go. Here's our right-hand rules. So our right-hand rules show that what happens is the electrons, when they get up here, they experience a force one way, and then they get down here and they experience a force the other way. And so the electrons move back and forth and back and forth and back and forth. That's called alternate current, or AC. Now, when electricity, we learned about direct current, or DC. So this is where you get the AC-DC phenomenon, which is more than just a great Australian rock band. Okay, AC current is just moving electrons that go back and forth and back and forth, and that's how our power plants work, and that's how our electric outlets work. Okay, so once again, as you can see here up at the top, all right, the electrons are going to get pushed sort of into the page, and then down at the bottom they get pushed out of the page, and so those electrons go back and forth as it spins, and you have electricity. Okay, so what are we doing with this electricity? Well, okay, we've created a force, and that force creates a voltage, and so now we have electricity. And here's the problem. We're burning these fossil fuels, or we're turning a wind generator, or we're using nuclear power to heat up water to create steam to turn a turbine. Okay, any of these things that happen, or falling water turns a turbine, any of these things happen, this is what's called a cyclical process or cyclical process. It's repeated, and anytime that happens, you'll lose energy to the surroundings. It's inevitable. Okay, you can't help it, and that energy loss is called energy degradation. It's the loss of energy when you convert energy from one form, like say chemical energy and oil, to another form, which is electricity. Okay, and every time you move energy, it changes. So now we have what's known as efficiency. And efficiency we studied last year with power. It's output power, which is what's useful available to us, compared to the input power, which is what was put in to get it. And efficiency is something that's very, very important when you consider alternate energy fuels, because a fuel that is inefficient, like wood, or is not going to be viable, because you need enormous amounts to produce your energy. Most of your energy is then wasted. Okay, so now we introduce what are called Sankey diagrams, and Sankey diagrams help illustrate degraded energy, input energy, and output energy, and they look like this. Okay, here's a very, very simple Sankey diagram. You have 100 joules of electrical energy goes in, and in this case, this is for a light bulb, a normal light bulb. 90 of the 100 joules, 90% of the energy for light bulbs is wasted. It's lost as heat energy, and only 10% of the energy that goes into a light bulb actually produces light. And so therefore, a light bulb is a remarkably inefficient device, which is why your parents are always after you to shut the lights off when you leave the room, is because they're being charged for the electricity that you're not using. Okay, I mean, even when you're in there, you're only using 10% of what they're paying for, and if you leave the room, it's a lot more. It's 100%. Here's a much more advanced Sankey diagram. This shows greenhouse gases, greenhouse gas production. So these are various forms of fossil fuels, and then the output of greenhouse gases compared to industry and transportation and commercial and residence. And again, you just see the input is here, the output is here, and then the degradation is down to the side. Okay? All right. So now we get into world energy sources, which is what you were talking about with your presentations on Monday. Now this slide here, this shows the different types of energy sources or fuels that you'll be responsible for. Okay? And what we have is some are circled and some are in rectangles, and they're written in two columns. The column on the left are renewable energy sources. Okay, these are ones that will not get used up. We will not run out of solar energy in the foreseeable future. Not something you or I or our great-great-grandkids need to worry about. Nor will we run out of wind, waves, tidal, biofuels. But stuff like fossil fuels, we likely will run out of those in the not-so-distant future. So that's considered a non-renewable resource. It takes 1 million years to produce it because it's created by prehistoric plants and animals being buried in the earth under huge amounts of pressure and breaking down into these fuels of coal or oil or natural gas. And well, we really don't have 1 million years to wait, or several million years. Nuclear fission is from uranium, which we dig out of the ground, and you have to assume that there's only a finite amount of uranium in the ground, and when we run out, well, we're out of luck. And then I have the rectangles are sun-derived. Okay, these are sources of energy that originated from the sun. So solar obviously is sun-derived. Hydroelectric is sun-derived because hydroelectric energy is essentially evaporated water, goes up into the atmosphere, falls on a greater elevation, and then we use a waterfall to collect it, to collect the energy. So again, without the evaporation, we would have no hydroelectric power. Wind is the sun creating different pressures at different points on the earth, and the air molecules moving from the high pressure to the low pressure, and that's what creates wind, and so that's essentially sun-derived as well. Waves is the same idea as wind. It's just different temperatures and wind produced. Tidal is from the moon, so that's not a sun-derived energy. But biofuels are from plants, and where do plants get their energy? From the sun. Geothermal is energy in the earth, and so that is not from the sun, nor is nuclear fusion, which is simply just two hydrogen atoms being fused together. Anyhow, let's move along and talk about an energy density options. Okay, energy, let's try that again. Energy density is the amount of energy available per kilogram of fuel. Okay, and this is something that you need to consider when you're using a source of energy, because obviously a society or a community needs X amount of megajoules or gigajoules to function, and so then you got to say, well, how much of this given fuel do I need to get that amount of energy? And so as you can see, stuff like garbage and manure, though it's environmentally friendly, you don't get a lot of energy per kilogram of burnt garbage or burnt manure. Wood, you get a little bit more. Coal, you really don't get very much, but there's a lot of it out there, and we have a society built to use it, which is to coal's advantage. Oil and natural gas, a little bit more, and again, we've built our society around it, so there's systems in place. Nuclear fission, you see, it goes up to 90 million megajoules per kilogram, and we'll talk about nuclear fission. That's the uranium nuclear reactors. You get a lot of energy per kilogram of fuel, but there are other risks involved with nuclear fission, and we'll talk about that. And then nuclear fusion at 300 million is a remarkable fuel source. Unfortunately, right now it takes more energy to make nuclear fusion happen than what we can collect from it, and so we aren't able to use it at a commercial or industrial level yet, and we'll talk about that as well. Here's a sample problem. Okay, so we have a coal power plant which has been given the task of providing 400 megawatts, so 400 megajoules of power per second to its community. Okay, but this coal power plant is only 35% efficient, so 65% of its energy is wasted, is lost as heat, and so with the given energy density of coal, they want to know how much fuel is consumed by the plant per second. So to solve this problem, we're going to start with efficiency. Okay, it's 35% efficient, and they've been tasked with providing 400 megawatts, 400 megajoules per second of energy to the community. And so they have to ask themselves, well, if I'm going to lose 65% of it, if I'm only 35% efficient, how much energy do I need to bring into the coal plant per second? And what the answer is 1,143 megawatts, or 1,143 megajoules per second. So that's how much energy has to be available for the plant for it to function. Okay, well, how much fuel is that going to take? Well, rate of consumption of fuel. Well, you have 1,143 megajoules per second are required, and each kilogram of coal will provide 30 megajoules of energy. So therefore, this power plant requires 38.1 kilograms of coal to be burned every second that it runs. That's a lot of coal, and that's one of the reasons that coal plants take a lot of heat, is because of the carbon dioxide produced and the environmental effects of digging it up. I think that's all I have for you today. What I'm going to get you guys to do, I want you to try some energy density problems in the textbook. Okay, I'm not sure of the numbers. You'll have to check. I'm sorry, I don't have a textbook here with me, but if I get my hands on one tonight, I'll email you. But in the meantime, it's not too hard to go to the back and back of the, not the back of the chapter, but back of the section that has energy density, and look for problems that have energy density and efficiency, and try and solve those problems. I'm hoping to be back on Friday. The doc says I just got to stay home today and tomorrow, and then he says if the virus and the fever is still there on Thursday, then I got to come back and see him again. But I'm really hoping it's gone by then. And like I said, if you have questions, I know it's not ideal, but email your questions and I'll get to you as quick as I can. Hope everything's going good over there, and we'll hopefully see you on Friday. All the best. Take care.